So I didn't really know what a tensor is, even though I went to engineering school. I watched some videos about it. I still didn't know what a tensor is. And then I decided to ask the smartest person that I know, and that person is ChatGPT. So this video just contains a longish interaction between ChatGPT and me, trying to figure out what the tensor is. There's a bit of a surprise ending to this, so you can fast forward if it's too long for you. I haven't decided yet about comments. We'll see if I allow any. But let me say this. I will, joking, I'll charge $50 for any comment that contains the words clear, easy, simple, obvious, or phrases like as can be easily seen, and similar expressions, because to me it's not clear, not simple, and not obvious. Okay, here we go now. Here is ChatGPT. I will start sharing. Okay, so I'm still struggling with tensors, I said, after watching yet another video not explaining it understandably. Can I say this? A degree K tensor is a K-dimensional array of numbers in which all numbers refer to a coordinate system with as many axes as there are rows in the tensor. ChatGPT responds, "You're very close, but there's a subtle misunderstanding in your sentence. Let's clarify and rephrase it properly. Here's a breakdown. What a degree K tensor really is. A tensor of degree or order K is not defined by being a K-dimensional array. Rather, it is an object that can be represented in coordinates by a K-dimensional array of numbers relative to a given basis, and that transforms according to a specific rule when you change the coordinate system basis." Fixing your sentence, your version. A degree K tensor is a K-dimensional array of numbers in which all numbers refer to a coordinate system with as many axes as there are rows in the tensor. Problems. K-dimensional array suggests the shape or rank of the array, like a matrix, is 2D, which is not always true. A rank 2 tensor, like a matrix, can be represented by a 2D array, but the general idea of a tensor is more about how it transforms under coordinate changes, not just about its shape. As many axes as there are rows mixes terminology from matrix layouts, not tensor structure. Better phrasing. Here is a corrected and clearer version. A tensor of degree K can be represented in a particular coordinate system by a K-dimensional array of numbers, and those numbers change in a specific way when the coordinate system changes. The defining property of a tensor is how it transforms under changes of basis, not just the shape of its array. Or more compact, a degree K tensor is an object that can be represented as a K-dimensional array of numbers with a specific transformation rule when changing coordinate systems. Would you like a visual example showing how a vector degree 1 and a matrix degree 2 change under rotation? That often helps this become clearer. I said yes. Here is the diagram. And I let this stand for a little while for digesting. On the left, you see the original vector, red arrow, and the tensor, blue dashed lines, indicating its actions as a transformation. Think of it as stretching ellipse. On the right, after a 45-degree rotation of a coordinate system, the vector has rotated as you'd expect, following the rotation matrix. The tensor has also changed, not just rotated, but transformed by RT to maintain its geometric meaning in the new coordinates. Key point, the tensor is defined not by its raw numbers, but how those numbers transform when the coordinate system changes. That's what distinguishes it from just any multidimensional array. Here the picture one more time. Can I see the rotation matrix? Yes, the 45-degree rotation matrix is as here, R equals, etc. If I remember this right from engineering school, these are cosine and or sine values of 45 degree. I didn't verify this with ChatGPT. This matrix rotates vectors and tensors counterclockwise by 45 degrees. What is RTR, I asked next. So in the definition over here, there was this RTR expression. The expression RTR is a transformation rule for a rank 2 tensor under a change of basis, like a rotation. Here is what each part means. T is your original tensor, represented as a matrix. R is a rotation matrix, here 45 degree counterclockwise. RT is the transpose, i.e. inverse of R, since rotation matrices are orthogonal, thus R inverse equals R transpose. RTR gives you the rotated version of a tensor, how it looks in the new coordinate system. Intuition. If you rotated your coordinate axis and you still wanted your tensor to describe the same geometric phenomenon, say stress or deformation, you need to update its components accordingly. That's what RT does. It gives the new matrix that represents the same tensor, but in the rotated system. Would you like to see the numerical result of RT for the specific example? Yes. The rotated tensor RT is as seen here. 1.5 minus 0.5 minus 0.5, 3.5. This matrix represents the same geometric transformation, stretching, shearing, etc., as the original tensor, but expressed in the rotated coordinate system. I ask, does every tensor represent a geometric transformation? Great question, and the answer is not necessarily. Here's the longer answer. Some tensors do represent geometric transformations. Yes, many rank 2 tensors, like matrices, do represent linear maps or geometric transformations. For example, a 2 by 2 matrix can stretch, rotate, or shear a 2D vector. The stress tensor in physics describes internal forces. The moment of inertia tensor describes how an object resists rotation. These can often be visualized geometrically and act on vectors. But not all tensors have a direct geometric meaning. Tensors are more general than just geometric transformations. They are multilinear objects that take in one or more vectors or covectors, linear forms, produce a number, and transform it in a very specific way under change of basis. So, for example, a rank 3 tensor might take 2 vectors and the covector as input and return a number. A metric tensor allows you to compute angles and lengths, but does not move vectors. These kinds of tensors are hard to visualize geometrically and don't correspond to physical transformations in space. Summary. Tensor type. Rank 2 tensor. Represents a geometric transformation, often yes. Example, matrix stress tensor. Rank 1 tensor. No, it's a vector or covector. Example, force vector or gradient. Rank greater than 2 tensor represents a geometric transformation, not typically. Example, Riemann curvature elasticity. Special case, metric tensor defines distance. Example, yes, but more abstract. Let me know if you want a picture or analogy for higher rank tensors too. So I decided not to respond yes to this one, but rather the previous definition contained the term covector, which I didn't know what it means. So I said, what is a covector? A covector is like the dual of a vector. It's a linear function that takes a vector as input and returns a number. In more detail, vectors. A vector is an element of a vector space, for example, a displacement in space. So a vector 3, 4. Covectors, also called dual vectors, or one form, is a linear map from an n-dimensional space of real numbers to real numbers. It eats a vector and spits out a number like a dot product. So phi of a vector v equals vector 1, 2 times vector 3, 4, which with the inner product gives 11. So here the covector is 1, 2, which you can think of as a row vector, but conceptually it's a different object. Analogy. A vector is an arrow pointing in space, for example, velocity. A covector is a flat sheet or field that assigns a number to each vector, e.g. a gradient. If you imagine wind blowing across a landscape, a vector field, then a covector could measure how much the wind pushes in a certain direction. In coordinates, if you're in Euclidean space with an orthonormal basis, vectors and covectors can look similar because the metric lets you turn one into the other. But in general, vectors and covectors transform differently under coordinate changes. Would you like a visual analogy for covectors versus vectors? I decided for this moment not to follow up on that and ask, why 1, 2 in this example here? Why 1, 2? This looks random. With a different covector, I get a different number. Excellent observation. You're exactly right, and this question gets to the heart of what a covector is. Why 1, 2? I chose 1, 2 just as an example of a covector. It's not special. It could be anything. Here's what matters. A covector is defined by how it maps vectors to numbers. Different covectors will return different numbers when applied to the same vector. So yes, if we define phi equals 1, 2, then phi of a vector v 3, 4 equals 11. But if we choose a different covector, say 0, 1, then psi of v equals 4. Each covector measures the vector differently, kind of like different sensors measuring different aspects of the same motion. Analogy. Think of a vector as a motion in space. Say you walk 3 meters east and 4 meters north. One covector might ask, how far did you go north? Another might ask, how far did you go northeast? Another might say, how fast are you moving in the direction of the slope of the hill? Each gives a different scalar answer depending on what it cares about. Summary. A covector is not tied to a specific number. It is a linear measuring device. When applied to a vector, it returns a number. That number depends both on the covector and the vector. Would you like to see a diagram where a covector is shown as a set of parallel planes, and the dot product counts how many planes a vector crosses? No, I didn't want that. It was at this point getting too complicated, and I didn't know what multilinear means. And I'm happy to say that if nothing else, after this interaction, I finally did understand what multilinear means. So let's get right into it. Great, let's clarify multilinear since it's fundamental to understanding tensors. Function is multilinear if it takes multiple inputs, vectors or covectors, and is linear in each input separately. Example, suppose we have a function t of uv that takes two vectors and returns a number. It is bilinear, a special case of multilinear if for fixed v, t of uv is linear in u. For fixed u, t of uv is linear in v. That means t of AU1 plus BU2V equals A times T of U1V plus B times T of U2V. It didn't exactly say that A and B are constants, but that's obvious to me. Sorry that I used obvious. The rest of the transformation sort of made sense to me. If t had three arguments and was linear in each, it would be trilinear, and so on. That's multilinearity. Tensors are multilinear maps. A tensor of rank 2 might be a function TUV that takes two vectors and returns a number. A tensor of rank 3 might take two vectors and one covector, T of UV phi, etc. A scalar is a rank 0 tensor, just a number. A vector is a rank 1 tensor, linear map from one covector or to one number. So tensors are multilinear maps from several vector and covector inputs to numbers. Editorial comment: note how different this definition is from the definition that we started out. Would you like a concrete example of a bilinear map with numbers? I said yes. Let's look at the concrete numerical example of a bilinear map, which is a simple kind of tensor. Set up, we define a function TUV using a 2 by 2 matrix. And TUV equals U transpose times M times V, where M equals this matrix here. Let U equals 1, 0, V equals 5, 6. TUV equals UT times M times V equals 1, 0 times the matrix 1, 2, 3, 4 times 5, 6, step by step. Multiply U transpose and M. U transpose times M equals 1, 0 times 1, 2, 3, 4, which gives you 1, 2. Then multiply with V. TUV equals 1, 2 times 5, 6 equals this stuff equals 17. What does this mean? The matrix M defines a bilinear map. It takes two vectors and gives back a number. The function is linear in each input. If you scale or add vectors in either position, the result scales or adds accordingly. Now I need something to drink. I'm losing my voice. Would you like to test linearity with the second vector to see that property in action? I say yes. Perfect. Here's what we did. Let U1 be 1, 0, U2, 0, 1, and V 5, 6. Let A equals 2, B equals 3. So at this point, we know that A and B are constants, even if we wouldn't have known it before when I said it's obvious. We computed T of AU1 plus B U2, comma V, which gives 151. And now we follow the linearity definition, pull out the A and B, and get 151 again. Result, they are equal. That confirms that TUV equals UT MV is linear in the first argument, which is one half of being bilinear. Would you like to also test linearity in the second argument, V? Yes. Excellent. Now we test the linearity in the second argument. Let V1 be 5, 6, V2 1 minus 1, U 1, 1. Let C be equal 4 and T equal minus 1. Then, so now we're leaving the first argument alone. We're testing linearity in the second argument. And you're getting 226. Now, if we pull out the constant C and D and separate the operations for V1 and V2, we also get 226. Result, they match exactly. Thus, T of UV with this formula is also linear in the second argument, so it's truly bilinear. And that's exactly what we mean when we say a tensor is a multilinear map. A tensor of rank 2, like this one, is bilinear. Would you like a quick diagram or summary slide on these properties? I said yes, but I'm not going to look at the summary slide here. Here's a visual summary showing how we confirmed the bilinearity of a rank 2 tensor. Each check confirms that the function is linear in one of its arguments, which makes it a tensor. Let me know if you want to explore higher rank tensors or how this connects to physics or geometry. Okay, now I asked. Geometrically, bilinear just means the mapping T is a plane, right? That's a very insightful guess, and you're almost right, but let's make the distinction clear. Short answer, no. Bilinear does not mean the mapping is a plane, but it does mean the output of a function TUV behaves like a plane equation in each variable separately. Why it's close but not quite? A linear function like f of x equals ax plus b or fxy equals ax plus by is a plane in 2D or 3D. A bilinear function t of uv, same formula as before, is more general. It's linear in u when v is fixed and linear in v when u is fixed, but not linear in both simultaneously. Concrete example, let's define t of uv equals u1 v1 plus t plus 2 u1 v2 plus 3 u2 v1 plus 4 u2 v2. This is bilinear, linear in u and linear in v. But now imagine plotting TUV as a surface over r to the 4th power. It's a function of 4 variables. If you try to fix v, then yes, T of u fixed v describes a plane in R2. Same thing for fixing u, but in general, the graph of TUV is not a single plane. It's a bilinear surface, a saddle shape if plotted over 2 variables. Say xy, with T of xy equals xy. Visual example. If T of xy equals x times y, that is bilinear, its graph is not a plane. It's a hyperbolic paraboloid, if I pronounce this correctly, a saddle shape. That's the simplest non-trivial bilinear function. Summary. Term linear, plane, linear in all variables. Bilinear, x times y, or u transpose times m times v. Graph shape is saddle, non-planar, linear in each variable individually, not jointly. Would you like me to plot a bilinear surface like txy equals x times y? I said yes. Okay, now here's the bilinear surface. I have to say, this really opened my eyes. That's where I understood. So if I imagine that I'm taking cuts of this, in two different directions, and every time in the cut plane there will be a straight line. So that would be linear, but obviously altogether this is nowhere near a plane. So it's not a plane, it's a saddle surface, positive in the upper right and lower left quadrants, negative in the other two. But if you fix x or y, resulting slice is a straight line which shows linearity in each variable individually. This shape is the geometric fingerprint of bilinearity. Let me know if you want to compare it to a true plane or try another bilinear form. At that point, I felt that part I understand, so I didn't say yes. I'm getting back to this. In the beginning, you referred to a tensor as an array plus a transformation rule. Okay. But in the second part, you suddenly refer to it as a function. So the original definition is incomplete. Secondly, the function takes as input a vector. But function is a very general term. In all your examples, the functions perform a matrix multiplication. So calling it a function is too general. Can you come up with a revised tensor definition then? Answer. You've pinpointed a deep and important tension in how tensors are described. Are they arrays, functions, or transformation rules? And you're right. A precise definition should be consistent and complete. Let's resolve this with a clear layered definition that accounts for all of it. Revised definition of a tensor, general and precise. A tensor of rank K over a vector space V is a multilinear map. T V star times V star times V times V times V mapped onto the real numbers, where the function where the function takes P covectors and Q vectors with P plus Q equals K. And the map is multilinear, linear in each argument. This abstract object is independent of any coordinate system. This is the true coordinate-free definition of a tensor. I should point out that it doesn't explicitly say that the stars, that there are P of them, and the non-stars, there are Q of them, but I conclude this. Now, in coordinates, array plus rule. When you pick a basis for V, the tensor can be represented by a k-dimensional array, e.g. a matrix or higher dimensional generalization. However, this array is not the tensor itself. It's just its coordinate representation. The actual tensor is the underlying function. And that array transforms according to specific rules when you change the basis. These rules preserve the invariance of a multilinear function it defines. Summary. What is a tensor? Mathematically, a tensor is a multilinear function that eats vectors and covectors and returns a scalar. In practice, it's represented by an array plus a transformation rule that ensures the object is independent of a coordinate system. Why matrix multiplication shows up in low dimensions, like rank 2 tensors, the multilinear function is naturally implemented via a matrix multiplication, but that's just a convenient representation, not the definition. Analogy. Calling a tensor a function is like calling a quadratic form a function. True, but we usually mean more than just function. Saying it's an array misses the fact that arrays change with coordinates. The real identity of a tensor is in how it combines vectors, covectors invariantly across coordinate systems. So, okay. Let me know if you'd like this restated in simpler or more visual terms, e.g. rank to example only, or connected to applications like physics or machine learning. Okay, so I insist on constructive learning. So I now restate what I think I have learned. Is this correct? A tensor viewed as a function takes two vectors as arguments and returns a scalar, will always return the same scalar, even if the coordinate system basis in which the vectors exist changes, because there's a transformation of a tensor into a new representation that neutralizes the change of a coordinate system. Yes, that is essentially correct and well articulated. With a very small clarification, it becomes spot on. Refined version. A tensor viewed as a function takes two vectors or a mix of vectors and covectors as arguments and returns a scalar, will always return the same scalar even if the coordinate system basis changes, because the components of a tensor and the components of the inputs both transform in such a way that their combined result remains invariant. Why this matters? The invariance under the change of basis is the defining property of tensors. The transformation of a tensor's component is not just a fixed, but rather an inherent part of what makes it a tensor. The reason that tensors are so useful in physics and geometry is because they express relationships that are true in all coordinate systems. Example, if T is a rank 2 tensor and UV are vectors, then T of UV, this formula, under the change of basis, T, UI, Vj, and Tij all change, but the sum, Ui, Tij, Vj stays the same. That's the scalar output. So yes, your statement is correct and captures the essence of tensorial invariance. Would you like this turned into a boxed summary suitable for a slide or lecture note? I said yes, but again, at this point, I'm not going to go through it. Here is a slide summary of the core idea. A tensor remains invariant in its scalar output under coordinate changes because its components transform in exactly the right way to cancel out changes in the input vectors. Let me know if you'd like similar box summaries for rank 1 tensors, vectors, covectors, or high rank cases. I said, I'm still not happy. Before you describe the transformation of the numbers of a tensor by the matrix multiplication RTR inverse, is that always correct, or is this an example? Your instinct is excellent, and you're absolutely right to question whether the transformation formula RTR-1 or RTRT for orthogonal matrices is a general tensor rule or just one example. Side comment, I did study inverse and transposed matrices in engineering school, so I can deal with this. No, it's not always correct. Note the bold letters that ChatGPT is throwing at me. It's a specific case for rank 2 tensors that act as linear maps. Let's break this down carefully. The formula RTR minus, this applies to a specific kind of rank 2 tensor, one that represents a linear operator, i.e. a function T from V to V. In matrix terms, you represent T by a square matrix. You change the basis via an invertible matrix R, then T transforms like this. T prime equals RTR minus. 2, if a tensor is symmetric and the basis changes a rotation orthogonal, then r minus 1 equals rt, and we use t prime equals rt r transpose. This is the case for many tensors in physics, e.g. the stress tensor, inertia tensor, where orthogonal coordinates are used. More general tensors do not follow this rule. A general rank 2 tensor with components Tij under a basis Ei transforms like sum of AKI, ALJ, Tij, or in Einstein's notation, Einstein was German, so it's pronounced Einstein, T prime KL equals AIK, AJL, Tij, where A is the change of basis matrix, and the transformation is applied to each index according to whether it's covariant lower or contravariant upper. Summary: tensor type, linear operator rank 2, transformation rule as given here. Symmetric linear operator, that could be rotation basis for orthonormal basis, T prime equals RT R transpose. General rank 2 tensor, T prime KL equals AIK, AJL, Tij, pure component transformation. And remember that this implies the sum. Conclusion. So the transformation rule, RT R minus, is a special case, not the general rule. The true rule depends on how the tensor's indices behave under basis change. Would you like a table of how different types of indices upper lower transform in general tensor notation? At that point, I sort of decided that if it's only possible to really explain this by invoking Einstein, then I'm probably not intelligent enough to understand it. But I plowed on nevertheless. So I ask, so shouldn't we include the general rule as part of the definition of a tensor? If so, can you write a better general definition of a tensor? Yes, and you're absolutely right again. The defining characteristic of a tensor is not just multilinearity or array structure, but precisely its transformation behavior under change of basis. So here is a complete general and rigorous definition of a tensor that includes the transformation law. Refined general definition of a tensor. A tensor of type Rs over a vector space V is an object that acts as a multilinear map. So note that this time ChatGPT actually tells me that this appears R times and this appears S times, which means that, again, previously I guessed correctly. That is, T takes R covectors and S vectors and returns a scalar and is linear in each input. It has components T I1, J1 to IR, JS in a given basis, transforms under a change of basis according to the tensor transformation rule. Here is the Einstein rule, except notice it got more complicated again, where AIP are the components of a matrix that transforms contravariant indices. I note a grammar mistake here. Components, well, maybe not. BQJ are the components of the inverse matrix for covariant indices. Lower, sorry, the upper were contravariant indices. And summation is over repeated, summation over repeated indices is implied. Invariant content. What defines a tensor is that no matter how the basis changes, its final output, a scalar like T of U star V, doesn't change because the transformation of components and inputs cancel out. summary suitable for a slide or textbook. A tensor is a multilinear map whose components transform under a change of basis by a specific rule. Each upper contravariant index is multiplied by the change of basis matrix, and each lower covariant index by the inverse. This transformation behavior is what defines a tensor, not just its function-like behavior or array form. So let's just look at this one more time here. So we have this transformation from this t to this t, and now I couldn't explain this in detail. There are too many indices here. Would you like a diagram showing how upper-lower indices transform under basis change, or a concrete worked-out example of applying this rule to a rank 1-1 tensor? I decided not to take ChatGPT up on that because I still don't know what the covariant and the contravariant is. I need examples for this. Perfect. This is one of the most confusing but most important ideas in tensor algebra. Let's break it down with simple definitions and clear examples. What is contravariant? A contravariant vector is a normal vector, like displacement, velocity, or force. Its components transform opposite to the basis change, hence contravariant. If a basis changes by a matrix A, then the components of a contravariant vector transform by the inverse. These are the upper index objects in tensors VI. So maybe I'm wrong, but I have a naive idea that if spacing in the coordinate system doubles, then I need to have the vector in order to make sure that it still expresses the same thing. This is wrong, don't shoot me. What is covariant? A covariant vector is a dual vector, aka covector for one form, like a gradient or linear form. Its components transform with a basis change, hence a covariant. If a basis changes by matrix A, then the components of a covariant vector transform by A itself. So omega prime I equals A ji times omega j. These are the lower index objects in tensors omega I. Notice we moved from these to omegas. I was wrong the whole time, and these are not these are news. Apology. Simple example. Suppose you rotate the coordinate system 90 degree counterclockwise in 2D. Let's see how a vector and covector behave. A vector v10 pointing right, now points upward, becomes v prime equals 0, 1. A covector, say measuring how much rightwardness something has, also rotates, but keeps measuring the same projection. ChatGPT did not actually show me the covector here. Concrete table, contravariant, example, displacement force, index type upper, transforms with inverse of basis change, appears in vectors, covariant, gradient, one form, index type lower with basis change, covectors. I think I already admitted that at this point I sort of lost the explanation. Okay, visual analogy. Vectors are arrows, contravariant. They move and change direction when the axis rotates. Covectors are sheets or level lines, covariants. They rotate with the axis, still slicing space in the same way. Would you like a diagram showing this behavior side by side for a vector and the covector under basis rotation? Yes. So here is the Here is the diagram in a second, but revisiting this the first time, I start feeling that the covector, if it's a sheet, then it's not actually a vector. Then why is it called covector? Maybe because the sheet can be represented by a normal vector. Yes, I learned this in engineering school. Okay. So here is the covariant vector and the contravariant vector. And the original contravariant vector is here in blue, and the rotated one here is in red. And then the covariant vector, well, that's these slices that the definition referred to. Here's a side-by-side visual. Left contravariant vector, the blue arrow is the original vector, the red arrow shows how it rotates when the basis rotates. Sadly, the diagram does not show the rotated basis, which would have made it much clearer. This is how vectors contravariant behave. They adjust to stay pointing in the same geometric direction. So then I would say that this is a, I don't know, 40-degree rotation. Then this x-axis and this y-axis will also rotate 40 degrees this way. And then the angle between the blue red arrow and the x-axis is the same as the angle between the blue arrow and this original x-axis, and the same for the y-axis. Right covariant vector, one form. The dotted blue lines show the original one form, e.g. measuring how far right you go. The solid red lines show the one form, how the one form rotates with the basis. It transforms directly with the coordinate change. So here are the blue lines, and they show how far right you go, but I admit I can't quite visualize this. I guess if the blue arrow is here, then it just means that I'm intersecting two of the blue lines, and maybe the same thing for the red arrow. Although, sorry, I don't quite see that. Maybe here, 1 and 2. But it seems that the red arrow is too short to do exactly that. Okay. By contrast, this contrast highlights why contravariant and covariant components transform differently. They preserve the same scalar measures by responding oppositely to basis changes. Let me know if you want the algebraic transformation matrices shown here too. I've never seen the word oppositely, but so it would seem to me that if the rotation of the blue arrow to the red arrow goes against the clock, then presumably this blue line here rotates into this red line here with the clock. And that could have been made much clearer by ChatGPT. Or maybe it doesn't make it clearer because I'm wrong. Okay, I don't want to see the algebraic transformation. I just wanted to know how can I make a video out of this. So I asked it, how can I save this whole long discussion into a file? Here's you can save the entire conversation. Okay, fine, not interesting. Now, I just wanted to go back one more time to the beginning, and this part of the conversation happened several weeks later. Can you show me an example of a degree-free tensor with numbers? So this is what I got. And here's a concrete example of degree-free tensor Tijk, with each entry computed as the sum I plus j plus k. The table shows two slices of a tensor for k equals 0 and k equals 1, where each 2 times 2 block represents Tijk for a fixed k. Let me know if you'd like a visualization of this tensor in 3D or another numerical example. So I said, yes, show me a visualization. So here we are. And, and you see that well, we don't have a fourth dimension to visualize this. So ChatGPT very smartly uses a color. So let me quickly verify this. So here I'm at the point x is 1, y is 1, z is 1. So 1 plus 1 plus 1 is 3. And indeed, 3 is yellow. And I can totally make sense of this. Okay. And now, should anybody actually have listened up to this point with all my slurring and stammering? And now comes a real punchline, because I haven't been in physics in some 40 years. And I was, in that sense, never really in physics. I was just a lowly electrical engineer who had to learn some physics to make sense of electricity. So I'm not in physics anymore. I'm also not yet in machine learning, I dare to say, but I would like to be in machine learning. I just confirmed one more time what I saw here. And yes, exactly, a degree-free tensor, also called rank-free tensor, can be thought of as a three-dimensional cube in its coordinate representation, or in my language, a three-dimensional array, which is what I start with if anybody cares to go back to the very beginning of this definition. So key ideas, yes. Tensor is an m times n times p array. Come on, ChatGPT, just admit it, it's an array. Each index specifies a position along one axis of its cube. The structure is like a stack of matrices. For example, two slices where k equals 0 and k equals 1, as you saw in the table in visualization. So, important distinction. The data cube array is just a coordinate-dependent representation. It's not the tensor itself. Okay. Well, what makes the tensor is that when you change the coordinate system basis, all the numbers in the cube transform in a well-defined way, and the underlying tensorial function stays invariant. Okay. So we've been digging through this a good 20 minutes. This is just a restatement of the basics. The transformation and the functional effect of the tensor. Would you like to see how a degree-free tensor transforms its components when the basis changes? Or perhaps how it applies to real-world problems like color images, fluid dynamics, etc. So I just wanted to hear it one more time and be really clear. Is this the case for n degrees also? Would the number representation of n-degree tensors require n-dimensional data to be visualized? I missed the B, sorry, which is of course impossible in the 3D world. Yes, you're exactly right again. I think this is the first time that ChatGPT says to me that I'm exactly right and not that I'm almost right, and here's how I'm wrong. So, summary. A tensor of degree or rank k, n, when expressed in coordinates, is represented by an n-dimensional array of numbers. So, a rank 1 tensor is a vector, is a one-dimensional array. A rank 2 tensor is a two-dimensional array. A rank 3 tensor is a cube of numbers. A rank 4 tensor is a 4D array, a hypercube of numbers. Okay. And the same for n dimensions. But starting at rank 4 and beyond, we can't visualize them directly in 3D or 2D. Instead, we visualize slices or use notations, animations, or dimension reduction, e.g. projections or principal components, or simply analyze them algebraically. Important, this is only about how tensors are represented in a coordinated system. The actual tensor, the multilinear map, exists abstractly and doesn't depend on visualization. The high-dimensional array is just one way to encode its values. Analogy, just like you can see a 4D object, but can reason about it mathematically, you can see a rank 4 or higher tensor, but you can store it as an array in memory, manipulate it with code, e.g. NumPy, PyTorch, use it to contract with other tensors, and produce scalars, vectors, etc. Would you like a symbolic breakdown of rank 4 tensors as a stack of cubes, for example? No, I didn't want this. So here's my punchline. When researchers in machine learning refer to a tensor, what do they mean? Excellent and timely question. In machine learning, the word tensor is widely used, but its meaning is usually much more pragmatic than in pure mathematics or physics. What tensor usually means in machine learning? In machine learning, especially in frameworks like TensorFlow, PyTorch, and JAX, a tensor simply refers to a multidimensional array of numbers. That's it. It's essentially an n-dimensional NumPy array, a container for data. Example, tensor shape, vector, e.g. a word embedding, one matrix, batch of 64 images, 3 color channels, 32 by 32 pixels, and batch of 10 attention heads, e.g. in a transformer. Let me not even start about attention heads. What it usually does not mean in machine learning, tensors in machine learning are usually not treated as multilinear maps. The components are not assumed to obey any transformation law under change of basis. Again, the components are not assumed to obey any transformation law under change of basis. There is no distinction between covariant and contravariant indices. There is no intrinsic notion of geometry or invariance. So while the term comes from linear algebra and differential geometry, in machine learning, it's been reappropriated to mean a general-purpose data blob with n dimensions. Why keep the term tensor in machine learning? Because it generalizes matrices and vectors. The operations, dot products, convolutions, reshaping, etc., generalize familiar linear algebra, and it sounds more flexible and powerful than array. If a researcher says we pass the input tensor through a convolutional layer, they almost certainly mean we pass an n-dimensional array, e.g. shape, batch size, channels, height, width, through a function that does numerical operations on its elements. Would you like to see a real PyTorch or TensorFlow example of a tensor definition and operation? And at that point, I didn't continue because actually, from the beginning, all I wanted to know was what does it mean when machine learning papers talk about tensors? And I took a gigantic detour through physics and math, passing Mount Einstein on the way, to actually come to the simple answer of what I wanted to know. And if you haven't fallen asleep at this point, then now's the point to actually stop the video. Thank you very much for listening up to now. I will stop recording.